Expecting you went through that dull opening, you would eventually arrive at another universe. There is already a connection between quantum computing and black holes. In this educational video, we explore a crucial and surprising discovery made by the James Webb Space Telescope inside a black hole, explained by none other than Bill Nye the Science Guy. A black hole is a star so enormous that even light cannot escape from it due to its immense gravity. The mysteries of black holes have puzzled scientists for years. However, thanks to recent breakthroughs, something truly remarkable has been observed. The supermassive black hole consumes what could be compared to one Earth every day. Get ready as we dive into the incredible details of this endless exposure and what it could mean for how we interpret the universe. Stars, at the end of their life, much larger and more massive than the Sun, run out of fuel and begin to collapse under gravity. Black holes are fascinating, and it was indeed a challenge to search for the first one, even though Einstein's theory of relativity predicted their existence. Unlike stars, black holes do not emit light on their own. Their size and spin are the only measurable properties we have. Visual evidence of black holes confirming their existence has only recently become available. Despite this, definitive confirmation of black holes was lacking for a long time. The first black hole, Sagittarius X1, was observed in 1964, but it took over 30 years for experts like Stephen Selling and Kip Thorne to agree on whether Sagittarius X1 was truly a black hole. Their observations confirmed its existence, but they were cautious about the lack of definitive evidence. Selling and Thorne were almost 100% certain that Sagittarius X1 was a black hole in 1975, and by 1988 they were 95% sure. Still, they waited until 1990 to accept verification when more observations provided sufficient confirmation. The initial discovery of Sagittarius X1 was made using 2 Geiger counters sent into space on a suborbital rocket, detecting a signal pinpointed to a system 7,200 light-years away. This system featured a massive blue giant star orbiting another colossal object emitting strong X-rays, which would make sense if it were a black hole. Much research has focused on Sagittarius X1 since its discovery, revealing that it has 3 times the mass of the Sun, making it the largest known stellar mass black hole found without gravitational waves. This discovery challenges long-standing ideas about black hole formation and the mass loss experienced by stars over their lifetimes. Sagittarius X1 breaks records in more ways than one, with its remarkable mass and the fastest spin speed of any black hole observed so far, approaching the speed of light. These characteristics defy the accepted pattern of black hole development. While definitive evidence of black holes has only recently been found, it is increasingly clear that they are scattered throughout the universe. Even if scientists eventually unravel all the mysteries of Sagittarius X1, the first of its kind, countless others still hold many surprises. Less than 2,000 light-years from Earth, scientists have discovered a dormant giant, the Milky Way's largest stellar mass black hole, Gaia BH3, with a mass several times greater than that of our Sun. Despite being the second closest known black hole to Earth, Gaia BH3 remained unnoticed until recently. Gaia BH3 was discovered by accident when scientists from the European Space Agency examined data from the Gaia mission, which maps our galaxy in 3D. The discovery of this dormant black hole, which isn't actively siphoning energy and material from a companion star, was a complete surprise. Typically, stellar mass black holes in our Milky Way have a mass several times that of the Sun, with Sagittarius X1 holding the record at 15 times the Sun's mass. However, Gaia BH3, with a mass of 33 solar masses, is still small compared to other black holes, such as the central supermassive black hole in our galaxy Sagittarius A*, which is 4 million times greater than the Sun. Gaia BH3 is the second nearest black hole to Earth, behind only Gaia BH1, which is 1,500 light-years away and has several times the mass of the Sun. Cosmologists now have more evidence to understand how stellar mass black holes form. Black holes that arise from the end of massive stars with lower concentrations of heavy metals are believed to be the source of these enormous stellar mass black holes. These metal-poor stars, primarily composed of hydrogen and helium, are thought to experience slower mass loss, leaving more material available to form large black holes when they die. Using the James Webb Space Telescope, JWST, scientists have discovered an incredibly red, very massive black hole existing in the early universe's shadow. As the universe expanded, This black hole took on a reddish hue 700 million years after the Big Bang. The light traveling toward us is redshifted, suggesting a thick layer of gas and dust surrounding the black hole. Lucas P. Finnell and A.V. Curve of the Benin College of the NAS Cosmology Group determined the black hole's mass using JWST data, finding it to be around 40 times the Sun's mass. This discovery stands out from the universe it inhabits, showing that the very massive black hole is quickly consuming the surrounding dust and gas, located about 12.9 billion light-years from Earth. This quasar was initially recognized by its red appearance. Quasars are formed when a large amount of material surrounds very massive black holes, forming a disk of gas and dust that feeds the black hole. The massive gravitational pull of the black hole disrupts this matter, creating extreme temperatures and causing it to shine. The light produced by quasars can be so brilliant that it eclipses all the stars in their surrounding galaxy. The JWST identified this very large black hole as a small point due to the massive amount of radiation it was emitting. Initially, the object was thought to be a strange star-forming galaxy, but color analysis supported the theory of very massive black holes. Its small size and very massive nature stood out from other quasars observed in the early universe. This discovery was made possible by gravitational lensing, a phenomenon predicted by Einstein in 1915. Einstein's theory of general relativity suggests that objects of mass bend the fabric of spacetime, which combines into a single entity called spacetime. This curvature creates gravity, and the larger the object, the more intense the curvature. The shape of spacetime also influences the light emitted by stars, bending it as it passes close to massive objects. This phenomenon, known as gravitational lensing, allows us to see distant objects that would otherwise be invisible. The JWST used this effect, supported by a galaxy group called SMX J7233, to amplify the brightness of distant galaxies and reveal the red quasar. This new information adds to the growing body of evidence that the early universe was populated with exceptionally large black holes, which can be millions or even billions of times heavier than the Sun. Since this phenomenon has been observed in various early universe black holes, it sheds light on the evolution of both the black hole and its host galaxy, as well as the relationship between the two. The classic chicken or egg problem, however, on a cosmic scale, remains unresolved. Did the universe or the black hole come first? How large were the first black holes, and how did they evolve? Scientists might have found proof that microquasars, which are black holes consuming companion stars, are enormous particle accelerators producing unexplained high-energy galactic radiation that hits Earth. These giant black holes consume material from nearby very large stars in binary systems, and some of the stellar matter is ejected as relativistic jets traveling at unimaginable speeds. Microquasars are smaller versions of quasars, both energized by very large black holes consuming nearby matter. In 1912, high-energy particles could hit Earth with energies reaching 10 to the power of 20 electron volts, significantly more energetic than particles accelerated at the Large Hadron Collider, the world's most powerful atom smasher. The theory suggests that very large black holes and microquasars are the universe's most extreme particle accelerators. However, evidence of microquasars accelerating particles to such high energies has only recently been confirmed using the High-Energy Stereoscopic System, HESS. Analysts identified exceptionally high-energy gamma rays from the jets of the most powerful microquasar in the Milky Way, establishing a link between cosmic rays and microquasars. The microquasar SS-433 produces high-energy gamma rays through its jets, which interact with surrounding matter, creating a shock front that accelerates electrons to extreme speeds. These gamma rays are a consequence of this interaction. SS-433 was the first microquasar ever discovered, located at the center of the W50 supernova remnant, affectionately called the Manatee Cloud. SS-433 has been the subject of extensive study for decades. The system consists of a white giant star and a black hole about 10 to 15 times the Sun's mass. They orbit each other every 13 Earth days, with the star's outer layers being stripped by the black hole's gravity. Some of this material forms an accretion disk around the black hole, while other parts are ejected as jets traveling at 26% of the speed of light. These jets twist in a thin pattern, forming the W50 supernova remnant and giving it the appearance of a giant manatee. The jets fade over time but return in a repeating pattern driven by the periodic motion of SS 433. The jets from the black hole also interact with the surrounding matter, creating a complex interaction between the black hole and its environment. This behavior makes SS 433 one of the most fascinating and enlightening objects in the study of microquasars and their role in cosmic particle acceleration. Despite SS 433 being the first identified microquasar, much remains unclear about how black holes accelerate particles to such extreme energies and their broader impact on the universe. Scientists use various methods, including indirect measurements, to understand these giant phenomena. For example, black holes can be observed through their interactions with neighboring stars and matter, as evidenced by the dramatic increase in X-ray emissions as material is pulled into their gravitational grasp. This phenomenon is crucial in understanding black holes and their impact on the universe, providing fundamental insights into the evolution and behavior of these mysterious objects. In the realm of black hole research, the new discovery of the most distant known black hole, an extraordinary 13.1 billion light-years away, has also expanded our understanding of these massive giants. This discovery, made possible by the capabilities of the James Webb Space Telescope, JWST, reveals an exceptionally massive black hole formed less than 1 billion years after the Big Bang. This early development challenges existing theories about black hole formation and galaxy evolution. Observations suggest that these early black holes may have played a significant role in shaping the structure of the universe by influencing the formation and development of the earliest galaxies. In addition to their role in galaxy formation, black holes have been linked to powerful cosmic phenomena known as active galactic nuclei, AGN. AGNs are characterized by incredibly bright outflows from the areas around supermassive black holes at the centers of galaxies. This outflow occurs when material from the surrounding accretion disk is heated to extreme temperatures as it spirals inward, emitting X-rays and other forms of radiation. Studying AGNs provides valuable insights into the feeding behavior of black holes and their influence on their host galaxies. These studies have shown that AGNs can significantly impact galaxy evolution by regulating star formation and distributing heavy elements throughout the galaxy. Recent advances in gravitational wave astronomy have provided a new way to test the properties of black holes. The detection of gravitational waves from merging black holes by observatories such as LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo has opened a new frontier in understanding these elusive objects.